Okay, hi everyone. Thanks for coming. My name is Timur Doumler. I work for JetBrains, where I work on the C++ front end of C-Line, which is our C++ IDE. And yeah, it's great to be back speaking at ACCU. Thanks for having me. I'll be talking today about class template argument deduction in C++ 17. And so that's one of the new features that we got in C++ 17. It's really cool because it lets you write shorter and cleaner code, which is great. But if you actually, it gets a bit weird if you start trying to figure out how it actually works, and there's a few unexpected things. So I thought it'd be worthwhile, going over this and really talk about this feature. So what we're going to talk about, not necessarily in this order, is how does it actually work? How do you use it if you use the STL, because the STL fully supports this? What are the pitfalls that you might run into? And then how do you use class template argument deduction if you have your own library with your own templated classes? Like, how does it work there? What do you have to be careful about? And then we're going to talk about deduction guides, which is another part of this feature, and some metaprogramming techniques that are useful if you're writing deduction guides, and try to come up with a few coding guidelines that might be useful if you're doing that. So we are talking about class template argument deduction. But what it really is, it's a form of template argument deduction. And template argument deduction is something that has been around in C++ for a very long time. So we have it in C++ 98 with freestanding functions. So if you have a templated function like this min function here, and then you call it, you don't have to specify the template arguments, right? So if you call this min function with a pair of ints, it's going to deduce min int. If you call it with a pair of floats, it's going to deduce min float. And if you have different types in your argument list, then you're going to get a deduction error. So this has been around for a very long time in C++, and I'm not going to go over how this works. So I hope you're familiar with that. What we really want to talk about is what happens if you don't have functions, but you actually have classes, templated classes. Now, in C++ 98, you couldn't do much, so you had to actually specify the template arguments. Like if you have a template class like std_pair, and you want to create one of those things, well, you have to specify the template arguments, which in this case is string and int. Now, in C++ 11, we got auto, so we can write this a little bit shorter using this idiom of these make functions. So pair has a make pair function, and then you can specify your arguments there, and then that's going to deduce the type that you want to instantiate, and then you can write auto, so you don't have to write std_pair with the template arguments. So this here would deduce const char star int, because the literal is a const char. If you want a string, what you can do in C++ 14 is you can add this little s over there, and then it's a string literal. Unfortunately, also, if you want to do that, you need to use this namespace. Well, that's just life. But what we actually want to write is we want to write this, right? Because it's obvious from the arguments that we're giving here what the type should be. It's a string and an int. So what we want to be able to write is, well, it's a std_pair, and then the arguments are obvious from the arguments of the constructor. So we should be able to not have to write that. And the good news is that in C++ 17, this is exactly what works. So you can write this code, and it's going to correctly deduce pair string int for you. So you don't have to write that. So it becomes shorter, more readable, and yeah, that's the feature, right? So we're done. Of course, we're not quite done because you want also to understand how this actually works. Now, I could refer you to the relevant part in the C++ 17 standard, which explains how it works, which is it's a section called overmatch class deduct. It's a bit of a dry read, so I'm not going to show that wording here. Instead, I'm going to kind of explain the basic mechanics behind it. And I think afterwards, if you actually want to know, so I'm not going to cover all the details that the standard says, but all the important bits. And if you then afterwards go in there and read that section, you should understand what it says. So basically, the most important thing, the way I like to explain this is that you have to imagine that if you write code like this, this deduction thing happens actually in 2 steps. So the first step is it's going to deduce the template arguments that you didn't write. And then the second step is it's going to actually initialize the object. So those are separate steps. This is not really surprising because it's the same with the function, right? If you write a function, you omit the template arguments, then first it's going to deduce those template arguments and then it's going to call the function, right? So it's pretty much the same, but with classes it's a little bit more subtle than that. Let's say you have a templated class, something like pair. So this is not actually how std pair looks like. It has lots more stuff in it, but it's kind of an oversimplification which is enough for our purposes here. So you have a templated class with 2 template arguments, and then you have a bunch of constructors. Now you want to instantiate one of those things like this. What does the compiler do with that? It sees, okay, you want to instantiate an object of type pair. The next thing it sees is pair is a template. You didn't specify any template arguments. So probably you want to do class template argument deduction. The next thing happens, this thing has a bunch of constructors. Probably you want to call one of those constructors. And this is where step 1 kicks in, which is the actual class template argument deduction. So how does the compiler figure out what you actually want to instantiate here? So it's going to look at those constructors. And let's pretend for a minute that those constructors are just functions. They're just functions. Let's just pretend for a minute that would be the case. Now we have some template arguments. Let's pretend those template arguments are template arguments of that function. Just for a minute. Now those are templated functions. So it's not the actual code you write. Like this code doesn't exist. It's kind of what the compiler temporarily does for you. And so it generates these templated functions from the constructors, and they're called the deduction candidates. And then if you have this call down there, well, we know how to deal with functions, right? So it's going to look at these functions and apply the usual template argument deduction and the usual overload resolution that we already have in the language to that overload set. And then you're going to get a match. In this case, it's the second one because you're using R values down there. So it's going to select the R value constructor. And you have a match, and you have done template argument deduction. So it has deduced that for this function that the arguments are string and int. And then, well, it's going to insert that down there. And then it's going to do what it would have done if you have written string int. So now we know that this pair is actually a pair of a string and an int. Right? It has been deduced for you. Step 1 is done. Yes, there's a question.
You go back there.
Yeah.
So I'm just wondering, does it actually do, so your second constructor, if you just put it, now you can put a template there, right?
You mean if the constructor itself also has templates, template arguments?
Yes, but what I'm saying basically is it's different here because before you put a template, this was a T reference, right, which would only bind to a R value reference. Now this actually binds to this for reference, right? So I'm just wondering, like, how is that handled in the assembly? Do you understand what I mean?
The R value reference has a different meaning inside a template than it does.
That's universal reference. When you say ref, reference the template parameter, it has a different meaning when you're doing template argument deduction. So I'm just wondering how that's handled here.
All right, let's maybe discuss this afterwards. Right.
That's a real code on the other slide at C.
So that's not code that you actually wrote. It's like magic code that your compiler does, and there might be a special rule for the case that you're describing. I'm not sure right now. So let's. Is it okay if you just? So it has deduced string int. You're done. Phase 1 is over. Now we're back to the code that you actually wrote, but now we know that this thing is a string and an int. So now what we can do is, well, we can actually instantiate this thing. So now it's going to actually instantiate template, call the constructor, and you have an object of type pair string int, and you're done. And that's it. That's how it works. and you have your pair of string int. Now, if you call it with L values, then it's going to select the other one. It's going to do the same machinery, but of course it's going to deduce the same types, string and int, and you end up with the same result. Any other questions about this so far? Everyone good? Cool. So this means that you don't have to write make pair anymore, right? You can just write pair. So that's great, because this make pair thing is basically a workaround for the fact that up until C++14 you could only do this with functions. So you had to use a function to deduce the class template argument. So it's kind of a hack, and now we don't need to use that anymore. So there are a few edge cases where make pair is still useful. For example, make pair, if you have a reference wrapper of T, then make pair will unwrap that and use T as the. So there's a few, we would say, rare edge cases where it would still be useful, but in 99% of the cases, you don't need make pair anymore. Same with tuple. You can instantiate a tuple with a bunch of arguments, and it's going to deduce the correct types for you, so you don't need to use make tuple anymore. Now, there's one important difference between class template argument deduction and function template argument deduction. So class template argument deduction is an all or nothing thing. So you have to specify either all of the template arguments or none of them. Except, of course, if you have template arguments with like default values, then that's still going to work. But what you cannot do is this. So you cannot say, well, I specify the first one, which is a string, and deduce the other three. So you can't do that. So as soon as you specify one template argument, this whole machinery is not going to kick in. So that's going to be a compiler error. But you can do that with functions, right? So you can do that with make tuple. So that's the other case where this is still useful. So with make tuple, because the function, you can specify string like the first argument, and then it's going to deduce the rest for you. All right, let's look at some other STL classes. Let's look at vector. So vector also has this feature, so you can give it a initializer list, and then it's going to correctly deduce vector int for you. If you use different types in that list, then it's going to say, well, you have conflicting types, so you're going to get a compiler error. So this is kind of what you expect. It's really nice. Of course, with vector, there's a trap. So vector has this other constructor which takes a size t, and then it initializes a vector with that many elements in it. So in C++14, if you write vector int v3 with curly braces, it's going to be an initializer list, so it's going to initialize a vector with one int, which is 3. If you use round parents, it's going to call this size t constructor, and then you're going to have 3 ints which are initialized to 0. So this is C++14. Now what happens if you omit the int and do this with class template argument deduction? Then if you write the curlies, it's going to do the deduction. If you use the round parents, it's going to say, well, you're calling the constructor that takes a size t, so you want to have 3 elements. But 3 elements of what type? Like, you didn't specify that. So you get a compiler error. Vector has another constructor, which is really cool. And now something magic happens. So if you have a range of integers, so like the first vector, it could be anything else, like any range of integers, then vector has this constructor which takes a pair of iterators, like begin and end. And if you don't specify the int, it's still going to figure out that those iterators are iterators to int, and it's going to correctly deduce vector int for you. How does that work? Right? So it has this constructor which looks like this, which takes these two iterators. So if you have a constructor that also has template arguments, if you remember back when we were talking about how this machinery works, when it's going to pretend that this is a function and have this a set of deduction candidates, it's going to actually concatenate them. So it's going to take the template argument of the class, and then if the constructor also has template arguments, it's going to put them one after the other. Now if you call it like this, with this class, then it's going to say, well, okay, so you're giving me two iterators, so I can deduce type of iterator. but you didn't specify t, so I still don't know what t is. So how is it able to figure this out? And this is another feature, which is the deduction guide. So in these cases where the compiler can't figure out with this machinery what the type is, but it's kind of obvious to you what the type should be, you can write the deduction guide. And this is a thing that looks like this. So it starts with something that looks like a constructor signature, and then you got this arrow, and then after the arrow you put like a specialization of the same class. So you're gonna specify, well, if you have this constructor signature, and that's gonna be one of those, it's gonna be added to these deduction candidates, and if this is the one that's going to be selected, then deduce the type after the arrow. So now this is new syntax in C++ 17. It looks a little bit like a trailing return type with the arrow, but it actually has nothing to do with that. It's like a new entity. It's not a class, it's not a function, it's a deduction guide. Yeah, and with that deduction guide, basically you're saying, well, if I get two iterators, then take the iterator trace, figure out the value type which this iterator points to, and initialize a vector with that type. And that works, and that compiles. And if you do that if you give it two integers, for example, it's going to say, well, it's going to select this deduction guide candidate, and then it's going to try to instantiate this thing, and it's going to say, well, integer has no iterator traits, so you're going to get a compiler error. So that's really nice. Of course, there's another trap here. So this compiles, but actually the order matters. So the deduction guide is only going to be considered for the code that is below the deduction guide. So if you flip around the order, then that's not going to work anymore. Because when you instantiate v1, the deduction guide is not there yet. So the order matters. If you flip it around again, it compiles again. So one thing that seems to be like a good recommendation is, because these deduction guides are really part of your class interface, because they kind of tell you you can instantiate this class like this, although they're not inside the class, they're part of this class interface. So probably they should go immediately after the class definition, because then you can be sure that whenever people use this class, it's going to use the same set of guides. Whereas if you have guides in other places, then it depends on where you instantiate this thing. The other thing about deduction guides is that they have to be in the same scope as the class anyway. So if you have a class which is in a namespace, the deduction guide has to be in the same namespace. Otherwise, it's going to be a compiler error. The other trap with this is that list initialization still has priority. Here's the question.
Can you go back a few slides where you showed that at the bottom some code would not compile, the factor into two integer arguments?
What, this?
How come it cannot deduce this as, always mix up the values as 43 times 42, or the other way around?
Yes, yeah, it can do that. I didn't mention that case yet. It's going to mention that later. If you have another constructor where this thing matches, it's going to use that. I will have this on a slide later. So here I'm just considering this one constructor. Let's pretend if we have only this constructor, then this happens.
It's not standard vector.
It's not standard vector, yeah. It's kind of, if you have this thing with this constructor, then this happens. We're going to talk about what actually happens afterwards. Like, I have a slide about that. Where were we? Yeah, list initialization has priority. So if you initialize a vector with a range and curlies, it's going to initialize it from that list. It's going to use that for deduction. If you give it two iterators, then it's going to use this deduction guide that I just showed. But if you then write this in curly braces instead of parents, then it's going to do list initialization, right? So then you're going to get a vector of iterators, which contains two iterators, which is probably not what you want. So you really have to be careful with the parents and the curlies. Yeah, it works the same with all the other sequence containers, so list, dec, array, whatever. With array, it also deduces the size for you. We're going to see later how that works. And they also have these range constructors, except for array. Array doesn't have that. with the same pitfall, like you should, if you want to use this, you should use the parents and not the curlies. And then there's set. Set also has both of these constructors, but set also has more stuff. So, you know, set has this extra template parameter, which is the comparison function, so you can specify your own comparison function, and that's a template argument. But actually the cool thing is that set also has a constructor that takes this comparison as an argument to the constructor, and it can deduce that as well. So you can actually write something like this, where you can give the set like a bunch of values and a lambda, which is your comparison, without any template arguments, and it's going to deduce that, yeah, this type of this lambda is your comparator. And then it also has this other constructor which takes a range in a lambda, so that's really cool. It really makes you go back to the STL and check out like what are all the constructors in there, and you know, they unlock all this stuff that you can actually write code without specifying the template arguments, and you can use all these different constructors. Map is a little bit different. So what you want to do with map, if you initialize it, you would probably want that you can write something like this, right? So you have string and int, and you have like pair, and you have two of them, and those should be the elements of your map. Unfortunately, that doesn't work, because these, if you have these nested stuff, then the pairs and the curlies, they don't really have a type, right? It's this thing in the curlies. Sorry? It's not an initializer list. It's something that would match an initializer list, but it's not actually an initializer list. So it doesn't really have a type. So it can't deduce the arguments for you in this case. So in this case, you actually have to specify the template arguments again.
Could you use pair in these places?
Yeah. So you could write map m of pair curlies, comma pair curlies. Yeah, you could do that. It also works with copy constructors. So if you initialize a vector from another vector, you also don't have to specify the argument. It's going to figure out, well, it's the same type of vector. But then again, there's a pitfall here. So if you look at the tuple, if you have the curly braces and you give it one tuple, it's going to select the copy constructor. If you give it two of them, it's going to select the list initialization. So the rule here is that list initialization has higher priority, but then the copy constructor has even higher priority, right? So if you use T2, then you get a tuple of string, but then if you use T3, then you're going to get a tuple of strings. So there's a little bit of an inconsistency here where if you have one item in the curly braces, it's going to do something else than if you have more than one item in the curly braces. And that's a bit annoying, especially if you write generic code where it's templated and you don't know how many there are, and it's going to do different things if it's one and different things if it's two or more. So that's another thing that you have to be aware of. But it also, so coming back to the feature, it works in lots of other STL classes, and most of the time you can actually just save a lot of typing. So one example, which I think is one of the most popular use cases for this, is if you have long type names like mutexes, and there's, for example, shared time mutex, and then if you want to lock it, you have to specify this thing, and in C++17 you don't have to do that anymore. So you save yourself a lot of typing. Because it's obvious, right, what it is. You're locking that mutex. So it's, actually in C++17 you shouldn't write lockguard, it should write scoped lock, which is another new thing in C++17. It does exactly the same as lockguard, but it's also variadic as well, so you can lock several mutexes at once. So yeah, it's kind of the better lockguard. So I expect that probably lockguard will be deprecated at some point in the future. It also works if you have no arguments at all. So if you have something like stdless, it has this default template argument which defaults to void if you don't write it. So now you can omit these angry brackets, and it's just going to deduce this void for you. In other STL classes, it kind of always does what you expect, right? So if you have an optional of an int, it's going to deduce that for you. If you have an atomic and you give it a value, it's going to deduce the thing for you. With complex, same thing, it's going to deduce complex double for you. Here's actually a little subtlety with complex. If you give the complex ints and you don't specify the template argument, then, well, it's going to deduce complex int for you. And actually the standard says that it's unspecified whether complex int is even there. So it is there on the 3 major compilers, but it's probably not even what you want, right? So complex int probably is not very useful in most cases. But that's what you get here if you write it like that. So this is an instance of this thing that if you use C++ 17, then all of a sudden all these classes that have been there before, they gain these extra abilities of being able to deduce the template arguments for you. And then sometimes what you get is not quite what you expect. So if you have a library, if you have template classes, and then your users switch to C++ 17, then they can write it with class template argument deduction, and you should probably go back to your library and see whether there's anything in your classes and your constructors where people could use it in unexpected ways, which were not possible before. So class template argument deduction is there, and you can't really do anything about it, right? And so you have to make sure that the interface of your class still makes sense, even if people now use this feature with those classes. Now with complex int, maybe some people say, yeah, it's actually fine. But there's other cases where class template argument deduction leads to really dangerous ways of using classes that were just not possible before. And an example of that is smart pointers. So this is kind of the prime example where class template argument deduction can be actually dangerous and damaging. So let's say you have a struct with some constructor, and then you have a shared pointer to it, and then you would maybe expect that you can write it like that. You give it a pointer to this citizen class, and then it's going to deduce shared pointer citizen for you, and that's not working. That's specifically disabled. So you have to use make shared here. The same with unique pointer. It's not going to deduce the template argument for unique pointer for you. You have to use make unique. And there's good reasons for that. So first of all, if you use make shared, then it's going to do one allocation, whereas the other one is going to do 2 allocations. So make shared in this case is not just a kind of different syntax, but it's actually more efficient. The other thing is that make shared has how do you call it, exception safety built in, right? So if the new thing throws, then, sorry, if the constructor throws, then you're not going to leak memory. So it has this extra safety built in, which the normal constructor doesn't. And the third thing, which applies equally to make shared and make unique, is there is this thing that if you have an array and you pass it to a constructor, it decays into a pointer, right? And then it means that if you had class template argument deduction on smart pointers, you could write like that. So you could give it a pointer to an array that would decay to a pointer to an int, and then it would instantiate unique pointer int for you. And then if that's out of scope, it calls delete on it and not the delete array, and then you're in undefined behavior land and things go really, really bad. So what we don't want to do is we don't want so this is a bug, and we don't want people to be able to write this easier. We don't want to make it easier to write this bug, which is the reason why if you want a unique pointer of array, for which there are good use cases, you have to specify it. So basically that's it. So class template argument deduction gives you your classes all these magic additional properties, and sometimes you actually don't want them because they're harmful. Specifically, it's the case if class template argument deduction could lead to wrong or dangerous code, if it would not instantiate what you want, like with the array case, or if it would lead to code that's actually less efficient than, for example, a make function, which is the case for shared pointer, or if it would just not do what you want. So these are the cases where if you have a templated class, you want to make sure that class template argument deduction doesn't actually work. So now the next question is, how do we disable it? Like, how do we make sure that it doesn't work? And there's many ways to do this. So I'm going to cover like 3 ways of how you can do this. So let's say you have a custom smart pointer class, right? This is a templated class. It has a constructor that takes a pointer. And then if you have this class in your library, and then your user switch to C++ 17, and you do nothing about it, then this line at the bottom will compile. You don't want this line to compile. So what do you do? The first strategy is an idiom which I don't think it has an official name. I call it the type identity idiom. So how it works is you specify this really simple struct which has a template and then it defines a member type which is just the same type, right? So it's a really stupid struct which just defines the same type. So you give it a template argument T and then it defines a member type which is just the same type T. So it's like type identity. It's the same type. This is not in the standard at the moment for weird reasons, but you're going to have it in 20. If you want to know more about this, you can check out this paper where I kind of go into more detail about this. So anyway, so this you have this helper struct, and then if you have this constructor, you can put it in there. So instead of writing T star, you write type identity T star, which is exactly the same type, right? So you didn't really change anything. But the difference is that now it's not just T, but in order to figure out that type identity T of T is actually the same as T, the compiler would have to actually instantiate this template and kind of figure out, yeah, this is defined as the same type. And in this case, we call it non-deduced context, which means the compiler is just not going to do that. So if it sees this kind of dependent type name while it's doing template argument deduction, it's going to say, well, it's some other type. I'm not going to try to deduce that other type thing and figure out what it is. So it's just going to give up. And it's going to say, I don't know what type that is. Deduction failed. And you get what you want. This line stops compiling. So this is really cool, this idiom, because it also works on freestanding functions. So you can use it for function template argument deduction. And you can also use it per argument. So it's kind of flexible. Another technique, what you can do is you can do it via member typedef, which is what more or less what unique pointer does. So instead of saying in your constructor T star putter, you can define it with like a member pointer type. And this is still going to compile. But now you can also do the same thing. You can define it as something that depends on another type, which is not going to be deduced because it's a non-deduced context. So for example, instead of writing T star, you can write like add pointer T. And then it's exactly the same thing, but it's not going to be deduced. And then you get again what you want. The line is not going to compile anymore. The third strategy is you can actually, and this is what shared pointer does, you can actually add another template parameter to the constructor itself. And then if you do that, then it's going to deduce U, but it's not going to be able to deduce T. So again, deduction will fail. So this is the third way how you can do this. Any questions about this? Yes?
Then is it possible for that to specify the deduction? I mean, if you want to
The question was whether it's possible to define a deduction guide?
Yes. I mean, in a case when you generally want to, from giving you the fine key, for example.
Yeah, you can write a deduction guide. You can, if you have a case where you have like a templated constructor and it's not going to be able to deduce that because of that, then you can write a guide and say, you know, if you have this constructor signature, deduce this other thing for me. That's possible, yeah.
Like you showed with the iterator.
Yeah, we're gonna have more examples. So we still have some time. So we're gonna look at more deduction guides actually. Let's do that now. Let's have some more fun with deduction guides. So you're gonna see like all the different ways in which you can kind of use those. So a really cool one is the one that std function has. So std function also works with class template argument deduction. So you can give it a function pointer like this foo, and it's going to instantiate it. You can give it a functor class like this bar. It's also going to work. You can give it a lambda. It's also going to work. And that's done with deduction guide. So let's look at the first one. So obviously class template argument deduction by itself wouldn't work because the argument that you give it is a function pointer, but the template argument for function that you want to deduce is the function signature. So you have to unpack that, like get the function type from the function pointer type. And that's not something that class template argument deduction does by default, but you can do it with the deduction guide. And it's a variadic one because, hey, yeah, why not? They can be variadic templates. So here's the deduction guide. You get a pointer to a function with some return type and some arguments, and then deduce std function with that function signature as the template argument. So that's the deduction guide. With the other two, you have to do a little bit more. So there's another deduction guide for the other cases where you have a lambda or like a functor object. It has to do a little bit more work because it has to check whether the type you give it has an operator, paren, like a call operator, and then it has to kind of unpack the return type and the argument types from that. So the guide becomes kind of more complicated, but I hope it's you can kind of see how it would work. And the other cool thing about these guides is that they work with SFINAE, right? Substitution failure is not an error. And now we come back to a question that someone here had earlier about the vector. So of course, you were totally right. If we have this a vector and it has this constructor that takes 2 iterators, and you call it with 2 integers, vector also has this other constructor, which takes a size t, which is how many elements you have, and it's going to end the default value, right? So, which means that if you instantiate a vector and give it 103, then it's going to create a vector with 100 3s in it, like a vector of int with 100 3s in it. So the cool thing is, if you have this line, then if you look at the constructor signatures, or actually rather at the guide, if you look at the guide is a better match for this than the constructor that you want to call. Yeah, you want to call the count, the size and value constructor. But the guide is a better match because these are 2 equal types, like 2 ints, and then this one takes 2 arguments which are of the same type. So it's a better match than the constructors that you can actually call. But then because the guide has this thing, well, deduce, iterator traits value type, and integer doesn't have iterator traits at all, it's going to not issue an error, but it's going to silently remove this deduction guide from the deduction candidates overload set. And it's going to keep looking, it's going to find the constructor that you actually want to call, and it's going to do the right thing. So that's going to work, and it's going to instantiate a vector of int. It's going to put 100 3s in it. Questions about that? Okay, cool. So, yeah, that does the right thing. And the cool thing is because deduction guides work with SFINAE, you can actually do more stuff with it. So let's say you have a vector and you have this iterator deduction guide, but you only want to, yes, Louis?
Does this mean that we, like from a company perspective, does this mean that we locked ourselves out of adding iterator traits for new types because that could break code like this that relies on SFINAE, whereas we usually, like normally we say we don't care about code that relies on SFINAE because it's just too crazy to do any changes.
Yeah, so if I understand your question correctly, this is the actual guide that's in the standard library, right? So if you have an iterator which doesn't have these iterator traits defined, then you would have to add another guide if you want.
Let's say you want to add iterator traits to it. That doesn't make sense, but for another type it might make sense.
All right, so I should probably repeat the question for the video, right? So you're saying like if you add iterator traits for int.
Yeah, now suddenly you break it.
Then you would break that case, yeah. So if you add iterator traits for int and define value type for it, then that's not gonna, so then you're gonna not select the size and value constructor anymore. Yeah, that's gonna break, yeah.
That's a bad thing.
Louis says it's a bad thing. Yes, but why would you define iterator traits for int?
Not necessarily for int, but if you take another type where it might make sense, I'm just saying that it's going to tie our hands really bad in the library relation.
All right, so the comment was that for int probably you don't want to do that, but there's other types where you might want to do that, and then that would make our lives harder because you might actually break code when we do this kind of stuff. And yeah.
Our job is just, that's just what I mean.
Yeah, I agree. Yeah, you're right. Let's discuss this later. Where were we? Yeah, so deduction guides work with SFINAE. So we can exploit that. Let's say we have this deduction guide which works with iterators, but you don't want it to work with all iterators. You just want it to work with input iterators. You don't want it to work with output iterators because, if you call this thing with, I don't know, a back insert iterator or something, then you don't want this to work. So what you can do is you can SFINAE the guide out based on some condition. So if you want to say this guide should only work for input iterators, you write a meta function that says, well, this is only well formed if the iterator is an input iterator. It looks a bit ugly. I'm really looking forward to concepts where you can write this stuff a bit better. But yeah, it works. Like it's your usual template meta programming thing where you have a meta function which you use an able if, and if the condition here is false, then this is just not going to be a valid type, and it's going to be silently removed by SFINAE. So, which means that, actually, yeah, I was saying earlier that that's the deduction guide for vector. It's this one. So yeah, you can really kind of customize your guides to only deduce stuff if you think that it actually makes sense in this context. Another case of this is std_array. So std_array also has a very interesting template deduction guide. So class template argument deduction works with array, right? You can give it like a list of ints, and it's going to deduce array int. Obviously, this is not going to work without a guide, because array also has the size. So it has the type t, but it also has the size as a non-type template argument. And the machinery that we discussed in the beginning, like how it works, is not going to be able to deduce the size as well. So you need a guide for that. So this is how you could do it. You could say, well, here's a guide. You have some arguments. So use the kind of first argument and deduce the element type from that, and then take the size of how many arguments you have, which is this size of ... operator, and then deduce the size from that, and then this is your array type. Now, this works for this line of code, but unfortunately it also would work for this line of code, right? So if you give it like a float and an int, with this deduction guide that would compile, right? Because it would say, well, here's the first one, which is the t, that's a float, so it's an array of float, and then I have one other argument, so size of ... 1 plus size it will be 2, so it's going to instantiate an array of floats, comma 2, and then you're going to have a conversion on the int to float. And you don't want that, right? Because it's not consistent with all the other cases where we do list initialization like that. Like if it doesn't compile for vector, it shouldn't compile for array, right? That would be really weird. But in any case, you can then say, well, let's SFINAE out this guide if it's not the case that all your arguments are of the same type. And that's, again, a meta function that you can write for that. You can write it in this really cool way with fold expressions, which is another C++17 feature. So basically, what you're saying here is, okay, we have this guide, and you want to deduce, t is the element type, and we still have this thing where it deduces the size, but only do that if all the arguments have the same type, right? And there's the meta function for that, which is same, which is going to be true if things are the same type. And because it's variadic, you put it in a fold expression, which is this bit. So basically, if is_same is true for all of the arguments, then enable this, otherwise don't. And this is how std_array's deduction guide works. So you can really do a lot to kind of customize these guides by using meta functions. Cool. Of course, there are more traps with this, so let's discuss some traps. So one trap is, so std_array is an aggregate. And actually, the rule is that aggregates, if you have any kind of aggregate type, they always need guides. So that's kind of, you could say it's annoying, but it's logical if you consider how it works. So if you have a simple aggregate, which is basically just a struct that has a bunch of members in it and there's nothing else, it's a simple aggregate type, so you can initialize it like this, where you use the curly braces and it's going to do aggregate initialization, so it's going to just initialize this with this and this with this, and that's working, right? That's just aggregate initialization. Now you would expect that, well, these are two strings, obviously, so if I omit the string here, then it should also work. But it turns out that, no, it doesn't. If you recall how a class template argument deduction works, it looks at the constructors and then it constructs the deduction candidates from the constructors. But an aggregate type declares no constructors, so there's no deduction candidates that you could use in this case. right? So this whole mechanism just doesn't work on aggregates. And which is why if you have an aggregate type, you always need to write a guide. Even if it's like really simple like this, you still have to say, okay, well, it doesn't have this constructor, so let's add the guide with this constructor signature which matches this thing. And if you see something like this, then deduce the obvious thing. But you have to add this guide if it's an aggregate. And then actually from this follows yet another thing, which is if you do this with parents instead of curlies, then it's not going to work. So if you use this and you use parents, then it's going to find this deduction guide and it's going to correctly deduce that you want to instantiate name string. So the first phase of this mechanism is going to succeed. It's going to say, okay, you want a name with strings, fine. But then the second phase is independent, right? The second phase is where you know what type you have, and now you just want to instantiate it. So, and then you have, well, name, and then you have parents, and then it's going to say, well, there's no constructor that takes 2 strings, right? So it's not going to compile. So you have to use the curlies. Another thing, so you need guides for aggregates. Another thing to keep in mind is that this mechanism of class template argument deduction always uses the primary template. So if you have a primary template and you have a specialization, the phase 1, which deduces the types, is not going to look into any of the specializations. So if you have this, where you have foo and you have a specialization which takes an int and it has a constructor which takes an int, and then you say, well, I'm giving it an int, so probably you want this, but it's not going to be found because it's not in a primary template. So this is just a compiler error. So this would match, but it's in a specialization, so compiler doesn't care. A more subtle case, this is a code snippet that Roger Orr sent me, which when I first looked at this, I found this confusing, but if you actually understand the rules, then it should be hopefully less confusing. So we have a primary template which takes a t, and then you give it an int, and then you have a specialization for int. What is this going to do? Anyone wants to answer that?
I give it a try.
Yeah.
It will reduce t to be int because it sees the primary template has a matching constructor, and the embedded function is actually having that int as a template argument then. And then it will figure out, oh, there's a specialization for foo int, and actually use the specialization for instantiating the argument.
Exactly. So I'm just going to quickly repeat that. Yes, so the phase 1, which deduces the template arguments, is going to look at the primary template. It's going to see, well, you're giving it an int, so it's going to instantiate foo of int. It's going to deduce foo of int. And then phase 1 is over, and in phase 2, well, we have a specialization for int, and that has a constructor that takes a double, so this int is going to be converted to a double. So it's going to use this one here. So this is a case where phase 1 uses the primary template, but phase 2 is using the specialization. So class template argument deduction uses the primary template for deduction, but that's not necessarily the thing that's going to be instantiated. So from this follows kind of a recommendation that if you have class templates with specializations, then the constructor signatures of your specializations should actually match the constructor signatures of the primary template. And then you're not going to be able to get into this mess. Peter has a comment.
Actually, the underlying mechanism is the same.
Sorry, maybe could we use the handheld mic for questions so I don't have to repeat them? Is that going to work or no? No. Okay, sorry.
You have to repeat my.
Then I'll repeat your question.
The thing is, the mechanism that happens here is the same that happens when you have function specializations of template functions instead of overloads, and you get all kind of problem with them as well. So it's the same problem here.
All right, so basically.
E551 for.
Okay, so Peter's comment basically was you have similar problem with functions where you mix function specializations and overloads, and you can check out P0551
where we forbid that for the standard.
Where we forbid that for the standard. Good stuff. All right, so yeah, keep in mind those rules, so make sure that you don't get into this mess. So actually, I think this is a general recommendation. Actually, maybe there is a case where you would want specializations where you have like different constructor signatures, but I can't actually think of one. And I can't think of any STL class that has something like that. So, yes?
I have an example if you want to prohibit the instantiation of a template like that. So like you have something, and you say, I have a specialization where don't do that. Then you would have things like...
Okay, so you would have something like that in a specialization if you want to prevent something from compiling. Yeah. But otherwise, I think it's safe to assume that, this is a good guideline. Unless anyone actually, I don't know, it's a question, like maybe someone knows a use case where this would be useful. I don't know. Okay, a few more things. I don't have many slides left, so we are kind of approaching the end. A few more comments. So class template argument deduction doesn't work just in declarations, like all the examples that you've seen before. You also get it in new expressions, and you also get it in function style casts, which is really cool because you can use it with this almost always auto idiom. So this is also extremely cool with this other thing that Roger talked about yesterday, where we have the temporary materialization conversion. So now it actually also works with classes that are not copyable. And you don't have to write the template argument. And so it's kind of cool. A trap. Class template argument deduction works when you're declaring objects. It doesn't work when you're declaring pointers or references to objects. So if you have a pair, you can omit it, but if you want to create a pair reference to that other pair, then it's not going to do class template argument deduction on references. Same with pointers. It's just not going to work. But then you don't have to do that because you can just write auto, and that's nicer anyway. Another trap maybe is that class template argument deduction doesn't work for nested types. So you can write vector and omit the arguments, but you can't write vector pair and then omit the arguments in the pair as well. So if you have something like this, then it's not going to deduce that this is a pair of a string and an int because it's nested. So what you have to do in this case is either you do it the old style way where you actually specify, you write out the whole type. That's obviously going to work. Or what you can do instead is you can put the pair, I think we had a similar example earlier, you can put the pair actually on the individual initializer lists, and then you don't have to specify, you don't have any angle brackets here anymore. But it's not quite as nice as the first line, but the first line unfortunately doesn't compile. Another thing, so we talked about smart pointers and where you want to disable class template argument deduction on smart pointers. That's actually not true. You only want to do that for the constructors that take a pointer. But smart pointers have other constructors which are really useful, and class template argument deduction should and does work for those. So if you have a unique pointer, you can obviously move it into another unique pointer, and then that's just a move constructor, and then you're not going to have to specialize it, specify it here, so it's going to deduce that for you. You can actually create a shared pointer out of a unique pointer, and that's also going to work. So if that's a unique pointer of citizen, that's going to deduce shared pointer of citizen. Then you can, create another shared pointer from that. You can create a weak pointer from the shared pointer. That's also going to deduce. If you do it the other way, it's going to also deduce it if you create a shared pointer from a weak pointer. Obviously, we need guides for that because we need to unpack the weak pointer, see what it points to, and then create a shared pointer with that type as the argument. So we have guides for that, which look something like this. Well, if you have a shared pointer, you construct it from a unique pointer. Well, kind of unwrap it, take this t, and use this t as the template argument.
It's not using the deleter? Yeah.
No, because it's not, the deleter is not a template argument of shared pointer, right? No, this is the deduction guide, but shared pointer doesn't have deleter here. Unique pointer does, shared pointer does not. The other thing that you might want to consider is that the guides are for deduction and the constructors are for actually constructing. And they don't have to match necessarily. So this is what the guide looks like, but the actual constructor looks like that, where in the end, if you actually construct it, you of course take this unique pointer by ref, and the guide doesn't have that. So it looks like, you would take this unique pointer by value, which is probably not a good idea if it's an L value because it's not going to work. But the guide is not for constructing. The guide is just for deducing. So you're not going to run into this problem of taking a unique pointer by value. And also the signatures of the guide and the constructor, they don't have to match because they're being used in different phases of the process. Anyone has questions about Louis?
What is the compiler actually, what expression is the compiler actually checking? If it tries to deduce that deduction guide from an L value, it's not going to work because that would require a copy of unique pointer, which doesn't work, right? So what is it kind of, I'm trying to figure out like what is it instantiating, right? Do you understand my question? Is the compiler trying to check the deduction guide?
So it's going to check it's going to use the deduction guide to create the deduction candidate, which has the signature. And then this is going to be selected by overload resolution. And then if that would be a constructor, that would obviously not work, but it's not a constructor, so it doesn't have to be well formed if you would actually call it like that. It just has to match during the overload resolution phase. And then it's just going to instantiate this thing, and then it's going to call this constructor where everything's great. Does that answer your question? Maybe there's a subtle detail in your question that I missed. So,
yeah, I think I just need to
yes.
Actually, that's a very common trick to use the by value deduction guide, let's say by value argument deduction guide to then later use the whatever overload you have with the R value reference or const reference or whatever.
Yeah, so the comment was this is a common pattern, and this, yeah, exactly, it's a common pattern. It's what the STL does. So you use the deduction guide with the value because that's going to match everything, and then you're going to use that to deduce it, but then you have the actual constructors which have more complicated signatures which actually do what you want.
And it's a nice feature because you only have to write one deduction guide.
And it's a nice feature, that was the comment, because it's a nice feature because you only have to write one deduction guide. And that's exactly the reason why you do it. Because if you write it like this by value, it's just going to match everything. So you don't have to worry about const, ref, whatever. And you wouldn't be able to, you wouldn't write a constructor like that because you couldn't actually call it. If it's an L value and it's not copyable, you wouldn't be able to call it. But you don't call deduction guides, right? You only use them for deduction. So you just write one guide with the value, and then it's going to match it, it's going to deduce the correct type, and then you're going to use the actual constructors, and you can have a bunch of them. So typically you have one guide like this, and then the constructors are like ref, const ref, or whatever other combinations.
That answers my question, thanks.
And Louis says it answers your question. Okay, that's great. Yeah, any more questions about this? Yes?
Can you write deduction guide for template functions also?
The question was, can you write deduction guides for template functions? And the answer is you cannot, as far as I know.
It's already doing that
Because-
since 98.
Because it's already...
But you have the deduction happening. You cannot have extra guide for it.
No, I think the question was whether you could bypass function template argument deduction, which we have since forever, and actually make it deduce something else by writing guides for the functions. And that's...
No, you write the function.
Yeah, you just write the function, exactly. So if you want that with the function, you can just write an overload. That's what you do, right?
I have to think about that. I'll ask you.
So you don't need this with functions, because you can just add more overloads.
It's the same mechanism as with function templates, the template argument deduction. It's already there since. The only thing you don't get, it's combined with overload resolution. That's why you shall not specialize function templates.
All right. Yeah. So the last thing that I want to say is that all the guides that we've seen so far have been templates themselves, right? You have template type name T, blah, 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 arrow. but guides don't actually have to be templates. So you could hypothetically do something like this, where let's say you have a templated class which takes any string type as the argument, and then you initialize it like this with string literal, and it's going to deduce widget const char star, right? And now you want to say, okay, well, yeah, that's fine, but whenever I give you a const char star, use a string view instead, because string view is awesome. So you can write a guide which would match just this situation, right? So it's not even a template anymore, right? So it's just like, if you match this constructor signature which takes a const char, well, then just instantiate it with a string view instead of a char. So I imagine that this opens up the door to lots of weird uses of deduction guides. And actually, in cases like this, I would actually recommend to not do that. So you can do that, but you shouldn't do that, because the problem is that it's not obvious from the call side what's happening, right? So if you understand how class template argument deduction works, and you write it like that, and you know this has like one template argument, which is this thing, and you give it a const char, and it's going to silently turn it into something else, that's probably unexpected for some of your users, right? So I would say this is bad practice.
The code is broken anyway.
No, it compiles.
Yeah, that's very dangerous.
Yeah, so this is dangerous. Yeah, this is like a very made up example, but I can imagine that you could do some stuff like that in real code, where you just write some guides like, oh, if you have this type, then just use this other type, in ways where it's just not obvious for the user, which didn't maybe read all these guides, why this is, or even if they did, like, it's just not like why. So the recommendation is, don't use deduction guides. Is the arguments that it's going to deduce, it's not obvious what they would be from the place where you call it. Right, so class template argument deduction is really, really great for saving you some typing and making code clean and short in cases where, well, I have this templated thing, I give it this argument, so obviously I expect this template argument to be deduced. This is what it's great for. In cases where it would not be obvious, I would say, don't use it. And the reason is, of course, that you want to write good code. This I think my favorite thing of all time is this, right? So this is what good code means, right? You read it and it does what you expect and you understand what it does. So we have all these new features in the language, and you should use them to reduce the number of WTFs and not to increase it. So yeah, that's the general message. Yeah, thank you, that's it. Questions? I think we have lots of time for questions. No questions? All right, well then I'll be here for the rest of the conference, so I'll be happy to chat about more weird things that can happen in C++ 17. Thank you for coming. Bye.